For lesson 2 in our new unit, we are focused on isosceles triangles and equilateral triangles. There are some concepts dealing with the angles in these triangles that we are going to be wrestling with. So we're going to apply theorems about isosceles and equilateral triangles to solve some exercises, and that should inform a lot of our work as we move through this unit on proofs. All right? And so first we want to make sure that we understand what isosceles and equilateral triangles are. And so here's kind of that summary definition where you have a pair of congruent sides, that's isosceles, where all the sides are congruent, that's equilateral. The plot twist today is knowing the relationship amongst those sides in a triangle is going to inform us about relationships amongst the angles. And so it's kind of a cute trick how this works within triangles. And obviously we need to know the triangle angle sum theorem, that the sum of the measures of the angles in a triangle is 180 degrees. If you recall lesson 3 of our second unit, we kind of had a rough time trying to add to equal 180, also including issues where we had supplementary angles, 2 angles that sum to 180 versus in a triangle 3 angles that add to 180. So we're going to be using this triangle angle sum theorem a ton in our classwork and also in our notes. So it would be in your interest to have a calculator handy for this. Also, considering the anatomy, if you will, of an isosceles triangle is going to be beneficial as we navigate through the vocabulary. The congruent pair of sides are referred to as legs of the isosceles triangle. The third side, the non-congruent side, if you will, is considered the base of the isosceles triangle. And this is a little bit of a misnomer because just because the base is on the bottom doesn't mean it always has to be. You can have an isosceles triangle where you have the 2 legs and then the third side is off in that direction. I kind of drew that like an equilateral triangle, so I'll try to do a little bit better job. But this could be the base even though it's not on the bottom, and that can be a confusing issue for some folks. If your figure can rotate, so now that's on the bottom, maybe that is helpful. So we use those transformations, those rigid motions from our previous unit to understand that orientation doesn't matter, all right? We still have the same characteristics, whether the base is not the bottom or if the base is the bottom. All right, so keep that in mind. If that is an issue for you or if you have questions about that, please feel free to ask. The vertex angle, the angle that is included between the congruent sides is referred to as the vertex angle. And the base angles are the pair of angles that include the base. These are the angles that are opposite from the pair of congruent sides. And that's a huge deal to be able to recognize which angles are the base angles versus the vertex angle, the congruent legs versus the non-congruent side, because we use those base angles in our isosceles triangle theorem, which states if 2 sides of a triangle are congruent, then the angles opposite those congruent sides are also congruent. So if we know that AB is congruent to BC, then that means I know that angle C is congruent to angle AA, all right? And there's also a converse to this. If 2 angles of a triangle are congruent, then the sides opposite those angles are also congruent. This is the converse of the isosceles triangle theorem. So if angle A is congruent to angle C, then that means that segment or side BC is congruent to segment or side AB, all right? So that's the isosceles triangle theorem and its converse, all right? So here is what a proof, it's kind of a messy proof, but it uses symmetry, it uses reflections, and it uses congruence that we discussed in our previous lesson. Here is kind of a step-by-step, if you will. It's not written out as a formal proof, but here we go. If we are given an isosceles triangle, then we can understand that there is a line of reflection, a line of symmetry within this triangle, such that when I reflect the halves of the triangle over themselves, or if I fold this piece over that line of reflection, then that means I have 2 triangles that are congruent to each other. ABD and CBD are congruent to each other. All right? If those triangles are congruent to each other, then that means that their corresponding angles are congruent to each other. Since these triangles are congruent, it means that the angles at A and at C are also congruent to each other. So that is kind of an attempt at the proof of the isosceles triangle theorem without using any of our special magical triangle shortcuts that we're going to learn about in lessons 3 and 4. All right? And so if we know that these sides are congruent, it means we know these angles are congruent. Let's put that to work. Here we have two situations where we are going to use the isosceles triangle theorem, and we are going to attempt to solve for x. In this triangle, we have these congruent sides. Draw that picture to the best of your ability. Label it example 2a. And if these sides are congruent, then we know that these angles are congruent. So this one is also 28 degrees, which means that we have this sum, 28 and 28 and 5x plus 9 add to equal 180 degrees. Again, in Algebra 1, you had the equation, your job was to solve for x. Here in geometry, we create the equation, and then we do Algebra 1, solve for x. So here we're going to have to combine some terms. We've got 28 and, we got 28 and 9 adds up to 65. Then I'm going to use the addition property of equality to add negative 65 on both sides. And then I'm going to divide both sides by 5, multiply both sides by 1/5 to find out what x equals. Now, knowing what x is means that we can find the measure of this angle here. All right, I'm not asking you to plug that back in to substitute and then evaluate for the measure of this angle. However, we use the isosceles triangle theorem to help us create this equation, knowing that we've got 28 and 28, create our sum and go from there. On this item, you could do this on your own if you'd like, or not. I'm going to go ahead and do it. You can pause the video if you want to try on your own. I am going to recognize that since this is an isosceles triangle, these base angles are congruent to one another. These angles opposite the congruent sides are going to have the same measure. They're going to be congruent to each other. So I'm going to add 4 x's to both sides. I'm going to add 3 to both sides. I'm going to divide by 12 on both sides to find out that x is equal to 1. All right? That triangle obviously not drawn to scale. That means that each of these angles is only 5 degrees. So it'd be a very, very skinny angle and a very, very obtuse angle up there. But here is the Algebra 1 process that we go through. Hopefully that went well for you. Likewise, using the converse of the isosceles triangle theorem, we want to make sure that we can understand which sides are congruent when we are given a pair of congruent angles. All right, so on this, I know that if these angles are congruent, by the converse of the isosceles triangle theorem, these sides are congruent. I would say that PR is congruent to QR, which means that the length of PR is equal to the length of QR, which means that x plus 20, substitute, is equal to 8x divided by 3. All right? Now, you do not need to write out all these steps, but it maybe is helpful for you to understand where our equation comes from. Once you have the equation, you are able to solve it. Multiply both sides by 3. Use distribution as needed. Subtract 3 x's from both sides. Divide by 5 on both sides, and you will solve for the variable. You go ahead and draw the triangle for letter B, as you did for letter A. I did this work, but I want for you to do that work. I will answer that question in class for you, but it needs to be in your notes, please. All right, moving right along, continuing our exploration of isosceles triangles. Here's something that you ought to know. If we bisect the vertex angle in an isosceles triangle, the segment that bisects that is also the perpendicular bisector of the base, meaning it makes right angles and it cuts the base into 2 congruent parts, all right, or 2 parts of equal measures. Please write this verbiage, draw these pictures if you will. Given this, we know that that is also true. All right, we'll explain the proof of this at another juncture. We will do that after our next lesson, actually. We're going to do a little bit of what's called side angle side shortcut on that. It's a little bit weird to have this before doing that, but you could also consider the fact that you have a line of reflection, BD, just like we did at the beginning of the lesson, and therefore these angles will be congruent to each other, these angles around point D, which also means if they are congruent and supplementary, that they have to be right angles. And if they're right angles, then that means that those segments are perpendicular to each other. Yay! Furthermore, we would know that these segments are congruent using the same proof we did at the very beginning of the lesson. All right? But here's how we will apply this. We will say, go ahead and draw that picture. We will say that we can use the information given to find the measure of angle RSQ, all right? We can figure out what that is. It's going to require a little bit of effort on our part. We're going to know if this is an isosceles triangle, that this angle and this angle are the same measure. So I know that 31 and 31 and the measure of angle PSR is going to add up to 180. Now, this is looking at the big triangle here. The big triangle. PSR is this whole thing here. So I know that I've got 62 plus the measure of angle PSR is equal to 180, or the measure of angle PSR is equal to 118 when I subtract 62 from both sides. And now I know that 1/2 of, this is unrelated, 1/2 of the measure of angle PSR is equal to the measure of angle RSQ. All right? Which means that I can take 1/2 of 118 to get the measure of angle RSQ, which is what I'm looking for here, which is going to give us, what, 59 for the measure of angle RSQ. There is a significantly faster way for us to do that. Instead of trying to find the measure of the whole angle and then cut it in half, we could use the fact that this is the angle bisector to know that these are going to be right angles. All right? And so if this is 31 and this is 31, if this is 31 and this is 90, these two have to add up to 90. And so you can either do 90 plus 31 plus, let's call that x, is 180. Or you can say 31 plus x equals 90. All right? Either take this equation and subtract 90 from both sides, or recognize the two acute angles in a right triangle are complementary. And so we can subtract 31 from both sides to find out that x is equal to 59. A couple ways we can do that. Finding the length of PR here does not have to be the world's biggest challenge. That being said, we do have to think about what we're doing. If this is an isosceles triangle and this is the angle bisector, not only are these segments perpendicular to each other, but also these two segments are congruent to each other, all right? SQ is the perpendicular bisector of the base, meaning that PQ is going to equal RQ, which means that the length of PQ will equal 4. Now, using segment addition from unit 1, PQ and QR is going to give us the total length of PR. So I can add 4's together and find out that the length of segment PR is 8. All right? I would expect you to be able to do that without having to show all that work. Okay? So I know that sometimes I show all the work and you're like, why do I have to write all that? You don't. You don't. On these, you need to write your equations. All right? I'd expect you to write equations and solve them when there's multiple steps involved. All right? But here, if you're looking at this and you're like, oh, that's 4. 4 and 4 make 8. You can do that in your head. Then you do not need to write that out. All right? That being said, if it's like a 2 or 3 point question and you solved wrong and there's no work, that's a little bit aggravating. All right, part 2. This is a long video. I apologize. We're at 13 minutes already. We're probably going to go for another 6, so this will be 20 minutes just like last time. On this situation, we have a quick review of equilateral triangles. And we know that triangles that are equilateral are also equiangular. We also know that if a triangle is equiangular, that it will be equilateral. That information is very helpful in us kind of exploring these triangles. We also know that in a triangle, that means that each angle is 60 degrees. All right? 180 divided by 3 angles of the same measure means that each one is going to be 60 degrees. All right? This information is critical for us to be able to do the work that we're going to do. Because we'll have an exercise like this where we're given a number in the directions, but no number is given in the picture. All right? And so what we're going to know here is that this angle CBD, draw that picture to the best of your ability, is 130 degrees. Our job is to find the measure of this angle. All right? This is what we are looking for. The measure of angle BAD. Now, how in the world are we going to do that when the only number that we're given is that this is 130 degrees? Well, the good news is that given an equilateral triangle, I know that each one of these angles is 60 degrees. And so if this whole thing is 130, then that means that this part has to be 70 using the angle addition postulate. We can write out formal equations saying the measure of angle CBD is equal to the measure of angle CBA plus the measure of angle DBA. To say that 130 is equal to 60 plus the measure of angle DBA, which means that 70 is equal to the measure of angle DBA. You can write out all that, or you can do it in your head and with a calculator and on the paper. All right, you need the drawing there to support that though. So if this is 70 degrees, and we are now going to focus on this triangle here, triangle BAD, we should notice that this triangle is extra special. It is not equilateral because we have a 70-degree angle, but it is isosceles, meaning that this is x and so is that. All right? So we have that relationship, and that is what we are going to be exploring. That's what we're going to apply to find the measure of angle BAD. I'm going to call this x degrees, and that x degrees, that's 70 degrees. I know that x and 70 make 180. At this point, I would expect you to create an equation and show work. Down here, if you did that in your head, that's fine. This part, show work, please. We create our equation, we do our algebra 1, we solve our equation. And that is the extent of that work that I would expect you to go through to say that the measure of angle BAD is 55. Okay? Make sure that you are able to draw the picture, understand what happens with this equilateral and this isosceles triangle. Just because this is 60 and this is 60 doesn't mean that these are both 60. All right? So keep that in mind. That doesn't necessarily carry over from one triangle to the other. It only works when we are within a single triangle, that angles opposite congruent sides are congruent. All right? That's within a triangle. All right, this one, I want for you to do. Take some time to draw that picture. Take some time to label what you know. And use the triangle angle sum theorem. Use a linear pair of angles there. And find the measure of angle PNO and angle NOP. You need to do this probably before you can do that. Enjoy. I'm going to go to the next slide though. Here is our summary. These are things that you probably knew already before coming to this lesson. This is brand new information, and it wouldn't be a bad thing to write it down again. That's your call, but this is obviously what's new. This might be new to you. This should be old news. But hopefully putting it all together is something that was that you were able to follow on this video. Hopefully now you can say that you are able to apply theorems about isosceles and equilateral triangles to solve problems.